morning, dear friends. The summer is almost knocking the door of Kanpur. You could see we have come back in T-shirts. Of course, today is cloudy. You never know, after this rain, again the temperature may fall, and you should not be surprised if you are again back with winter clothes. That's the beauty of weather. The climate can change, and you are all aware that there is a huge changes in the climatic conditions, and this also has an effect on how the aircraft is going to fly. If you are flying through cloud, there will be a different type of response the aircraft will have for same type of control. So we need to take care of the airplane considering what is happening outside. And one of the way to handle is appropriately designing the stability of the airplane and also appropriately designing the control power. Okay? So far we have developed 6-DOF equation of motion. We have also used Laplace transform to get equations in frequency domain. And we have seen for a linear system, if I apply Laplace transform, then those differential equations I can convert into linear algebraic equation, and which are easier to solve. But that is a part of computing. But what is more important for us is what information we get from all those big equations. Before we go and start handling those equations which are developed in frequency domain, where primarily we have developed equation in longitudinal motion, and we have seen that it has two modes, predominant modes. One is short period, that is, if disturbance is given, within a short period it comes back to equilibrium. And there is a phugoid mode, where almost the angle of attack nearly remains constant. It's an approximation, right? But what is important is it is a long period motion. It goes like this. There's a apparent conversion between kinetic energy and potential energy. All these things we have done. Now, at this point, I'll put a hold on it. We'll come back to the simple thing before again you go back there and try to extract maximum information. So we'll take a pure pitch case. Pitching motion, you know, it's about y-axis, right? So pure pitch. And pitch, you understand, it is basically about, this is the x, this is the y, this is the z. Pure pitch is about y-axis, and it's positive pitch if nose is going up, negative pitch going down like this. So it has a pitch rate q, positive, q negative. Okay? And we know by now that the CL is function of alpha dot q delta E. Right? For a highly maneuverable airplane, you can see that the CL will be function of other state variables also. Maybe they are rates, maybe the control derivatives, rate of control derivatives. But we have taken a simplified case where we are modeling CL as function of alpha dot q and delta E. Similarly, Cm we express as a function of alpha dot q and delta E. And then we have become expert. We write CL as CL naught plus CL alpha into alpha plus CL alpha dot into alpha dot C by 2u plus CL delta E into delta E. And you know that when I write any rate derivative, because simply alpha dot or q, they are radian per second, but we want to use in a non-dimensional form. So for q, we have written qc by 2v, and for alpha dot, we have written alpha dot c by 2v, because alpha dot c by 2v and qc by 2v are non-dimensional. This part we have cleared. Now Cm, also you write as Cm naught plus Cm alpha into alpha plus Cm alpha dot into alpha dot C by 2u plus Cm delta E into delta E, right? When you talk about pure pitching means it is only theta is changing, or there is a Q, okay? And the moment I say theta is changing, it has its own effect. Let's say for an airplane, if I change the theta, the angle of attack will change. So there will be a change in the force in the z direction, in the x direction, and the airplane center of gravity may start moving up. But here, when you talk about pure pitch, only 1 degree of freedom we are talking about. We are not allowing the model to go up and down. It's only allowing the model to do this theta variation. Okay? Is it clear? Pure pitch is no such motion, no plunging motion is allowed. It's only the angular rotation about y-axis is allowed. But in actual practice, for an airplane, if I give some sort of deflection of elevator, not only theta will change, it will also generate a situation where, because of alpha change and alpha dot change, it will have motion in the vertical z direction. That is being neglected in pure pitch. Only angular motion is taken into account. So typically, if I try to simulate this case, I can equivalently say that in a tunnel, in a wind tunnel, I have put this aircraft model, right? And this is this model is fixed here, and the bearing is such that it will only allow this motion. It will not allow any plunging motion. So this is typically, I am simulating a pure pitch. Pure pitch. Let us see what does this mean practically. Remember, we define, if this is the airplane, we define this is our axis, and let's say this is the velocity vector and this is the horizontal. Right? What is this angle? This angle is the velocity vector making with horizontal, and that is the flight path angle. So this is gamma, the flight path angle. What is this angle? This is the angle between the axis, let's say chord, and the velocity vector. So this is alpha, angle of attack. So what is this angle? The angle between axis and horizontal. This is nothing but theta, where theta is the pitch angle. Clear? Gamma was angle between velocity vector and horizontal. Theta is the angle between axis, which let's say chord axis with theta, with horizontal. So that is theta. And alpha is the angle between velocity vector and axis. Okay? So this is the definition, and you know from here, theta equal to gamma plus alpha. Okay, so in actual free flight, whenever there is a control input which changes theta, it also changes alpha as well as gamma in general, right? Because if there is theta change, the alpha change. Alpha change means moment will come, the force will come through CL. So that will also change the motion of the CG of the airplane along z axis. So gamma will change. So all these things are representation of an actual flight. But what happens in a tunnel? If I am doing tunnel, you see this is the velocity vector. So velocity vector never changes, direction never changes, right? Relative wave velocity, it doesn't change. So gamma is 0. For a pure pitch, gamma is 0 implies theta equal to alpha, or theta dot roughly equal to Q and equal to alpha dot. And you know, in a tunnel, theta dot is definitely Q, because there are no psi or any such motions are there are no bank angle, nothing is there. So I can strictly say in a tunnel, theta dot is truly Q and Q is truly alpha dot. Right? Okay, so what the motion we are trying to study is, if I disturb a model on an aircraft model in a tunnel, if I give it elevator deflection and try to see how is theta or alpha going to vary, and from that response we would like to find out what is the natural frequency of this motion as well as what is the damping the aircraft is having. Right? So what we are trying to find out is what is omega n and what is zeta, and you are very aware of omega n and zeta. Omega n is the natural frequency and zeta is the damping ratio. We have all discussed in previous lectures, earlier lectures. So we are trying to simplify and try to see that can we get some feel so that we need not always work with a big equation as a designer. As a designer, it's important that we have smaller expressions, handy expressions, so that we can get the initial estimates. Right? Now think of a situation, if this is the tunnel and this is the model, this is the elevator, this elevator down is delta E, this is the CG and this is the wing and vertical tail here, rudder here. Right? If I give an elevator deflection and this is being exposed to a constant velocity v, or let's say u, or simplify, then how do I write the equation of motion? We are talking about angular motion. So angular motion so it is the moment that will decide what is this moment. This is the pitching moment. This is the pitching moment. And this pitching moment is about what axis? It is about the y-axis. So this is x, this is y, and this is z. We are talking about pitching motion about y-axis. We are also putting a condition that we are talking about small disturbance. Because why small disturbance? If I give larger disturbance, then it is very difficult to expand CL as linear combination of all this, because that time the flow and the aerodynamics become non-linear. So one condition also we are putting, we are giving small disturbance. And that was the basis of small disturbance theory, whatever we have developed earlier. So we are not violating from that. Also we now assuming that wing is, say, symmetric. Right? And for simplicity, we take Cm not equal to 0. It's just for algebraic simplicity. Right? So now, since we are talking about moment and pitching moment, you know this moment is equal to I y into q dot, because we are only talking about this motion. There are no other thing coming from yaw rate or roll rate. Right? It is only pure pitch. So I can write m equal to Iyy q dot. And what is m? I know Iyy q dot equal to moment is half rho v square s c bar into Cm alpha into alpha plus Cm alpha dot into alpha dot c by 2u plus Cm q into qc by 2u plus Cm delta E into delta E. Correct? Note that here Cm naught I have put 0 only for algebraic simplicity. You can put Cm naught and go on doing your analysis. So let me erase this part. So using this equation, I can write q dot equal to half rho v square s c bar by Iyy into Cm alpha into alpha plus Cm alpha dot into alpha dot c by 2u plus Cm q into qc by 2u plus Cm delta E into delta E. Right? So I can further write simplified, I can write q dot equal to m alpha into alpha, m alpha dot into alpha dot plus mq into q plus m delta E into delta E. What I have done? I have clubbed this. half rho v square SC bar Iyy into Cm alpha as m alpha. So what I have done, m alpha equal to half rho v square SC bar by Iyy Cm alpha. Similarly, what is m alpha dot? M alpha dot is nothing but, again, half rho v square SC bar by Iyy into C by 2v or 2u into Cm alpha dot. Correct? Half rho v square SC by Iyy, C by 2u, Cm alpha dot. That becomes my m alpha dot. So what is mq then? Mq is from here, again it is half rho v square SC bar by Iyy into C by 2u into Cmq. Correct? You can simplify this by doing some sort of algebraic operation. The v square and v is there, so it becomes 1v. That I leave it to you. So it is very easy now for you to know what is m delta E. M delta is nothing but half rho v square SC by Iyy into Cm delta E. Right? So you allow me to write this q dot as this, where this m alpha dot, mq and m delta E, they are referred to as dimensional derivative. So m alpha, mq, etc. are known as dimensional derivatives. In contrast, if I write Cm alpha and Cmq, they are non-dimensional derivatives. It is obvious that if you see the dimension of m alpha, you will find, yes, indeed, it has a dimension. Okay? You can check yourself by putting all the dimension. So we are writing pure pitch equation in a longitudinal motion. So pure pitch means we are talking about longitudinal motion. Restricted only theta, degree of freedom. So no plunging motion is allowed. And also we are implicitly assuming it is at constant speed, right, or velocity, because we are simulating a case of pure pitch which can easily be simulated in a tunnel. But pure pitch easily cannot be simulated in an open atmosphere, because the moment you give some deflection, there will be plunging motion as well, right? But there is a definite meaning of why we are looking for pure pitch. You will see that if this plunging motion is not really much, then a lot of information I get from this equation, simple equation, in terms of natural frequency of that mode as well as the damping ratio. And that is why we are doing this. So now I take Laplace transform. So with initial condition 0, and you know all these things very well. So we are talking about linear system, and it doesn't depend upon the initial condition. So by putting initial condition to 0, it doesn't change anything. We have discussed this in the last few lectures. So I write this SQS equal to m alpha into alpha s plus m alpha dot into s alpha s plus mq into q of s plus m delta E into delta E of s. And you know very well alpha s means the Laplace transform of alpha, which is in time domain, right? You know that. We have taken the Laplace transform here because this equation was in time domain. We are converting into a frequency domain using a Laplace transform, and you could easily see that this was differential equation and this becomes algebraic equation. There is a ease of operation. Now here we will do a little trick. What we will do, we know Q is equal to theta dot for a pure pitch, and theta is equal to alpha for a pure pitch, because if it is only motion like this, then whatever theta is there, that is only alpha, isn't it? Because this is alpha 0, theta 0. If I have theta like this, theta, this angle between the axis and the horizontal becomes theta, but similarly the angle between the velocity vector and the axis become alpha, so it is theta equal to alpha. So again you can check it. If this is a tunnel, if I have moved the model like this, then this is my axis, say chord line, and velocity vector remains like this. So this is alpha, angle between velocity vector and the chord line. Okay, and also you know theta is the angle between the axis and the horizontal, and incidentally velocity vector and horizontal are same, they're parallel, so this becomes theta also for a wind tunnel simulated case, which indirectly means if gamma is 0, that is theta equal to gamma plus alpha. So it says if gamma is 0, that implies theta equal to alpha, and if gamma dot is 0, this implies theta equal to alpha dot. What is the physical meaning is, if the disturbance is so small that it doesn't really create large plunging motion, then this approximation will work very well to get some relevant understanding about natural frequency and damping ratio, which is our target. So we are not very far off from here, because we are talking about small perturbation, and that is where this simple equation has got so much of meaning, right, for a designer. Okay, so we come here. So now from this relationship I can write Q is equal to alpha dot and Q dot equal to alpha double dot, right? I repeat here, since theta equal to alpha and Q is theta dot, so Q equal to alpha dot and Q dot equal to alpha double dot. Why do you want Q dot? Because you could see here, there Q dot was here. If I substituted alpha double dot, we would have got S square alpha S, right? Anyway, so there are many ways of doing, but you should be clear about this understanding. Now here, I will write the whole equation in terms of alpha S. So this will be S. For Qs, I can write, from here I can write Q of S equal to S theta of S, and that is equal to theta of S is alpha of S. I can write S alpha of S. Is it clear? Q equal to theta dot. So Q of S is equal to S theta S, and theta is I'm writing alpha, so S alpha S. So what happens here? So for Qs, I write S alpha S, so it becomes S square alpha S equal to M alpha into alpha of S plus M alpha dot into already S is there. So this is alpha S. For MQ, I write plus MQ. For Q of S, I again write S alpha of S is plus M delta E into delta E of S. That's all. Okay, let me write it again so that you understand, because I could see so many terms going here and there. Let us write it again. So let me write like this. S alpha of S is equal to M alpha into alpha of S, no problem, plus M alpha dot into S alpha of S, no problem here, plus MQ into Q of S, then M delta E into delta E of S, right? But we know that Q of S, already have seen, Q of S equal to S alpha of S. S alpha of S. Generally, it is customary to use S in a small cap, but for clarity, I'm writing like this. So what do you get? We get, oh, this is not alpha S, please understand, this will be Q of S. Okay. This is SQ of S, come back here. SQ of S equal to M alpha into alpha S, M alpha dot into S alpha S, plus MQ into Q of S, plus M delta into delta E of S. But what do you know? Q of S is equal to S alpha S, right? Simply I'll put there. So what will happen? This will become S square alpha of S, because Qs is S alpha S. So S into S become S square, alpha S, this is sitting pretty with S M alpha alpha S, and this is M alpha dot S alpha S, and then for MQ, I'll write MQ, and what is Q of S? Q of S is S alpha S. So again, I write here S alpha of S plus M delta E into delta E of S, that is the expansion. So if I now do one trick, I take this term left hand side, then what I get? I get S square minus M alpha dot S minus MQ S square minus M alpha dot S. This is S square. So M alpha dot S alpha S. So I'm trying to take alpha S common. Okay. So for this S square, for M alpha dot I bring it here. So this will be S M alpha dot. MQ I'm taking here. So it will be MQS. Okay. Now M alpha I take it here. So it will be minus M alpha. This equal to M delta E into delta E of S, right? Let me write it a little differently now. So I write it as S square minus MQ plus M alpha dot S minus M alpha. This equal to M delta E into delta E of S. Let us not forget again, what are these M alpha dot, MQ, M alpha, M delta E? They are basically dimensional derivatives. When I think of M delta E, immediately I know the non-dimensional derivative is Cm delta E. That is, what is the increase in Cm because of elevator deflection, whose sign is negative. And that is, this is dimensional, but Cm delta E is non-dimensional, right? So you know these expressions. So now I can write this as, here alpha S has to come. Okay, so I can write as alpha S by delta E of S is equal to M delta E by S square minus MQ plus M alpha dot S minus M alpha. Okay? We have seen almost similar looking term in a complex manner in our Sixth-Dorf equation. This is a special case of Sixth-Dorf equation of motion. What we will do in the Sixth-Dorf stability matrix, we will put those simplifications so that it results in a similar expression for pure pitch. So before we go to those exercises, we are trying to understand what is a pure pitch and how does it help us. Now what is this alpha S by delta S? This is conventionally known as transfer function. Okay. Now if you want to find out natural frequency and damping ratio for pure pitch longitudinal motion, this is very, very straightforward. You know that the characteristic equation is S square minus MQ plus M alpha dot S minus M alpha equal to 0, right? This is the characteristic equation, S square minus MQ plus M alpha dot S minus M alpha equal to 0, and I compare it with second order system, S square plus 2 zeta omega n S plus omega n square equal to 0. If I compare, then I get omega n square is equal to minus M alpha and 2 zeta omega n equal to minus MQ plus M alpha dot, right, because this is 2 zeta omega n S. Okay. So what is the natural frequency? Natural frequency is under root of minus M alpha, and you could always see the zeta will be equal to minus MQ plus M alpha dot, right, divided by 2 into omega n, which is nothing but minus m alpha. What a neat expression, right? You may wonder, this omega will become complex. Is it true? No, because if you see m alpha, what is the expression of m alpha? That is nothing but half rho v square s c bar cm alpha by I y. That is m alpha. Now, for a statically stable airplane, cm alpha is negative. Sin is so, m alpha sin is negative. So, this negative, when you put negative into positive, so omega and you get a positive number. So, no confusion or no conflict. Okay? This is a very simple way of handling a pure pitch motion through modeling, and we'll check when you'll be solving the 6th equation of motion, and you'll be getting a solution for some motion closer to pure pitch, how much they come close. And that way you can take a decision, especially in the design stage. You don't want to solve those big equations because you don't have complete information. So this sort of understanding makes you very comfortable, because you know the zeta you want maybe 0.6 or 0.5. So immediately you can see what is the MQ required, what is the M alpha required. If I want natural frequency of 13 hertz or 10 hertz or 2 hertz, I know what sort of configuration is required for me, and quickly I can find out those derivatives. But understand, this whole is for motion, longitudinal motion, angular motion, right? In aircraft, you will find damping and natural frequency of different modes will be required. Okay? It only addresses this, which you will see is fairly close to a short period excitation. So today we have just made an attempt to understand a pure pitch motion and how to compute natural frequency and damping ratio. And you will see that how handy is this when you will be getting some information related to natural frequency and damping ratio using our 6th equation of motion in frequency domain. And you will also appreciate how wonderful these approximations are for a designer, and designer life become very comfortable. Otherwise, he has to handle with big metrics. He doesn't like that. To start with, when I try to configure an airplane, I want simple things. I should be able to have a feel. I should be able to smell the numbers. Not that I have to wait for a computer to give me some number in decimals. No, that's not design I look for. Design I look for pure understanding, good approximations, relevant approximations, and get a concrete number. Okay? So with this, I am just ending. We'll come back to this again. Right? You'll see how beautifully this can be used for designing a stability augmentation system, which is lifeline for all control systems. Thank you very much.